Okay, the payoff here is a potential energy versus change in potential energy versus delta Y function. For an engine operating between 300 and 370 K, 370 Kelvin, the question is, what's the optimal height to which to raise the water? Okay, do we raise it to 1 meter? Is it better to raise it to 0.9 meters? Do we get more change in potential energy per unit of thermal energy or heat that we put into the system? Okay, so let's think about this for a minute. If we raise the water just very little, we're not going to get very much potential energy increase. If we don't raise the water at all, we won't get any potential energy increase. So if we raise the water to height 0, we get 0 potential energy increase because we're not raising anything. The water ends up at the same height it started. So there's no potential energy increase, even though we have to put heat into the system. Now we're going to get maximum expansion of the gas if we don't raise the water, okay, because we don't need to do anything to build the pressure. The whole 300 to 370 Kelvin temperature change will expand the gas at constant pressure, so we'll move a lot of water. But we're not going to be moving it up. There's no potential energy change. Now, if we make the tube long enough, we can get up to 370 K at the same time the water gets to the top of the tube. And since we can't go past 370 K, we're not going to have any expansion. So that the water will get to the top of the tube, but no water is going to come out. So that we're not going to have raised any significant amount of water to get a change in potential energy. Now you might argue, well, the water in the tube has some potential energy. Remember, this is a thin tube. We can think, at least in the ideal case, of the tube being as thin as necessary to make that potential energy of the water in the tube essentially 0. So that for delta Y, at the maximum height to which we could raise water between these two temperatures, again we get no potential energy change. So between no potential energy change here and no potential energy change here, we will have positive potential energy changes because we will be raising the water at least a little bit, and we will be expanding the water at least a little bit. So the change in potential energy will be positive for every delta Y between here and here. Now I've just drawn a very simple curve, and it looks kind of symmetric, but that's just because that's the easiest way to draw a curve between here and here. Okay? Whatever the curve is, whether it's skewed this way or skewed this way, or if there's some weirdness in the curve, maybe it maximizes at 2 points or something. There will be at least one point, though, at which we get a maximum potential energy. And you can go to your theoretical results in calculus, mean value theorem, intermediate value theorem, and so forth. If we assume, as certainly must be the case here, that this function is continuous and 0 here and here, there's got to be a point where it's maximum. Point where the slope equals the average slope, etc. And that's just intuitively obvious. So we could say that. Now I say, okay, V1, well, actually that's not even relevant. I'm not going to mention that yet. Okay. Now, the temperature T1, temperature T in state 1, is what determines how high the water is raised, and so that determines how much difference you have between T1 at the intermediate temperature and the 370 degree Kelvin temperature, which determines two things. It determines how high the water can be, because T1 will determine how much pressure you can get, and it determines how much expansion there is at constant pressure, so it determines the change in potential energy. So there's a definite relationship between the intermediate temperature T1 and the potential energy change. It's not a linear relationship. It's a little more complicated than that. It's not overly complicated. It's not that difficult to understand, but there is a relationship, okay? So that we could equally well represent the potential energy as a function of T1. Potential energy being a function of T1, well, I was going to talk about a composite function there, but it's going to be easier to understand that if we actually get the functions. Okay, so the point is that between 300 Kelvin, if T1 is 300, then that's the same as the initial temperature. You've built no pressure, the water's not going to be raised. You're going to have maximum expansion, but no potential energy change. If T1 is 370, that means you raise the water as high as you can, ending up when the temperature is 370 before you expel any water. But now if the temperature's already hit the maximum possible temperature, you're not going to have any room for expansion, any temperature change for expansion, and you're not going to get any expansion. So again, same argument basically, you're going to have a curve here. Now, if this curve is symmetric, this isn't. If this curve is symmetric, this isn't. And it's probably likely that neither curve is going to turn out to be symmetric. But if we can express this potential energy in terms of the temperature T1, then we can take the derivative of that function with respect to T1, determine this critical point, and if necessary, verify that this is a maximum, but that's going to be very easy to do. It's probably a good idea to go ahead and do it, okay? And compare that with what happens when we actually do this experiment, which we're going to do in the very next lab, which this semester is tomorrow. So we have this situation, we have the mystery of what's this potential energy function, but if we follow these steps in the analysis that we just did with numbers and do it with symbols, including probably symbols for the 300 and 370K, Tmin, Tmax, and leaving the volume as a variable, we're going to get a function that we could apply to any such heat engine and figure out how to maximize the temperature, the PE is a function of temperature, and then see if that mimics what happens when we actually do this in a lab. That we're going to raise water to different heights using the same initial and final temperatures, and try to determine at what height the potential energy is maximized. Compare that with the result of a theoretical analysis.